All right, so I started the recording, and the date is 6/22, and today we're going to be talking about arc length. And then later on, we're going to be talking about surface areas using arc length and rotating them around axes. So before I really get into what arc length is, I want to talk about what integrals are doing and why you see them in other things other than just area. So what exactly do these integrals do? Before, you're kind of taught that it's just this area underneath the curve, but that's not exactly what they do. What do? They sum, so they're sums, right? They're sums over small intervals. And this is useful because we're going to kind of talk about how we get to arc length and what it means. So when you get further and further into Calc, you'll kind of realize that you start with any kind of finite approximation. Like, for instance, you guys learned how to do Riemann sums and stuff like that to approximate integrals. Well, as you make the rectangles smaller and smaller and smaller, you eventually get to what the integral is going to be, right? So you take some kind of approximation, and at infinity, so like a very, 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 very small rectangle, and you're adding up all these values of the function, that gives you this area underneath the curve. So using this kind of idea as some kind of approximation, and we're going to take smaller and smaller these intervals and then sum them up using integrals, we get some kind of answer. So let's go ahead and first try to approximate arc length here. So let's say we've got some kind of curve like this. I draw something like this from this A to B, right? The best way to kind of approximate this guy, well, I shouldn't say the best way. The easiest way is just take these 2 points and have a straight line and find the length of that line. But that length of the line can be easily calculated, right? It's a distance formula, right? So let's go over here, and we're going to call this point right here point 2, and down here point 1, right? So our distance here, I'm going to call D, is given by the distance formula. So the coordinate of the x coordinates, their difference, and then the difference of the y coordinates, both squared and square root, right? Because this is just like Pythagorean with this triangle up here. So that's not a very good approximation, but at least it's something. So what happens if we go ahead and try to do something a little bit better? So I'm going to draw another graph here. Same function, right? But now I'm going to put 3 points. Now it doesn't look too much different because that point's right down the middle, but see what happens when we do this third guy here. Something like this. I'm going to put points on the end and then break it up into thirds. And then we approximate that. Now, each one of those has a distance, right? We have to use this distance formula to find the length of each of those straight lines. Another way of writing this D is the square root of the change in x squared plus the change in y squared. Well, what ends up happening if we keep making smaller and smaller intervals, right? So we're using, let's say we're using 5, and then 10, and then 20 intervals, all these different points on this curve. These like delta x's and delta y's are getting smaller and smaller and smaller until we have let's say we finally get to an infinite number of these points, right? If we get to an infinite number of these points, what we can do is say that this kind of approaches a delta x becomes a dx and a dy, right? Well, another way of writing this guy right here is I'm going to factor out a dx squared. So I get a dx on the outside of the radical. I get a 1 here. And then this term becomes a dy over dx. Square this guy. And that looks a lot like our arc length formula from the book. But that's only for one little small segment that's really, really, really small. So how do we rectify this? Well, we take an integral. And the integral is the sum over small intervals, right? So if we take an integral of this, we go from a to b, and now I'm going to call this f prime dx. This is equal to my arc length, which the book calls L. Now, if you go back up to the line above, you can see that we can factor out a dy instead of the dx. And that leads us to another way of how to write arc length. So now we're going to do it in terms of dy. So we're going to go from c to d, and then the square root of 1 plus. And now we're going to have dx dy here, right? So this has the function equation solved for x, and then you take a y derivative, and then you can use this form, right? And later on, we're going to see the benefits of using either one based on what kind of function we're looking at, especially later on when we're doing revolutions with this. It might be a lot easier. So why don't we go ahead and look at our first example. So number 1 is I want you guys to try to see if you can find the arc length. I'll give you guys a few minutes of the natural log of secant x. And we're going to go from 0 to pi over 4. So I'll give you guys a few minutes, and then we'll start to try to go over it. It's not too bad. I think this is a pretty easy one. Okay, so the very first thing we should start to look at here is our y prime. Right, so we've got y prime here, and to the integral out, we've got 1 over secant of x from the natural log, and then the interior. Then take the derivative of the inside. We get, this is times secant of x times tangent of x. And those secants are going to cancel, and we're going to be left with tangent of x, right? So with that, we can write L from 0, integral from 0 to pi over 4 of square root of 1 plus tangent squared x dx. And that radical is really nice, right? If you recognize it from our trig subsections in practice, we can get that this is just secant of x dx, right? And with that, we know that the integral of secant is the natural log, the absolute value of secant x plus tangent x. And this is evaluated from 0 to pi over 4. So with all that, plugging that in, we're going to get the natural log the square root of 2 plus 1. Right. So this is a pretty easy one. The integral, the derivative turned out to be pretty nice, and then plugging it in to the radical portion simplified a lot, right? So this is a good opener. So I'm going to go ahead and start writing number 2 down, and you guys can go get started on that. So we've got now x is equal to 2/3 times y minus 1 to the 3/2, right? And we're going to go from 1 to 4 in the y direction. So this time we're using the y definition for arc length. So the first step you should be taking is finding the derivative and plugging it into this radical, and start setting up your arc tangent or your arc length integral. Okay, so we can write x prime here as, luckily enough, the exponent when it comes down cancels with that coefficient. Right, so we have y minus 1, the 1/2 power, right? And then that means that we've got L is equal to the integral from 1 to 4, square root 1 plus this y minus 1, because we have the square root and then we're squaring it. So just got that guy. Dy, then this is equal to the integral from 1 to 4 of just the square root of y dy. That means we got 2/3 y to the 3/2 evaluated from 1 to 4, and that gives us 14/3. All right, so this is another pretty straightforward one. It's chosen so that it works out pretty nice. So let's move on to the third one here. So I'm going to go ahead and write problem 3 down. And give you guys a few minutes. So we have that x is equal to 1/2 y squared. And we're going from 0 to 1/2. All right, so find the arc length. All right, so let's find x prime first. Pretty easy. It's just y, right? So setting up our arc length integral, we're going from 0 to 1/2 of square root 1 plus y squared dy. Right? And if we've got that, then this looks a lot like a trig integral, right? So what we're going to do here is I'm just going to go through the beginning steps because I'll explain them a little bit. So we've got y is equal to tangent theta. So then we have dy is equal to secant squared theta d theta. So we can rewrite our integral once we get our bounds. So we go from 0 to 1/2. And now in these theta coordinates, we're going from 0 to pi over 4. So this becomes the integral from 0 to pi over 4. And then we've got 1 plus tangent squared theta secant squared theta d theta. This just becomes the integral from 0 to pi over 4 of secant cubed theta d theta. Now this integral can be solved using integration by parts, so I'll give you the setup for this. But I think we're going to try to move on to some of the other stuff. So if we set u equal to secant of x, and we set dv equal to secant squared x dx, you can do integration by parts on this integral. What ends up happening is it's one of those trig integrals when you do two iterations of integration by parts, you're going to get the same integral back with some other terms are just floating around, so you can solve for it and you have the final answer. It's one of those like rotational kind of integration by part problems. So you can do this twice, get the original integral and solve for it. But we're going to kind of move on to more arc length stuff and more rotational stuff. But I will give you what this guy comes out to being. This is equal to 1/2 secant theta tangent theta plus natural log secant theta plus tangent theta. And this is all evaluated from our original bounds, 0 to pi over 4 and the trig theta bounds. And then plugging that in, we get 1/2 times the quantity of square root of 2 plus the natural log 1 plus square root of 2. All right, so now that we've got arc length down, let's start talking about this surface area. So in the next section, right after arc length, it uses the concepts of arc length to develop kind of what we were learning with rotating areas, but now we're rotating this arc length and then getting surface areas. So the book kind of describes how it comes up with this equation. They start off with the area of a cone as pi r times L. And on page, you want to follow through that, 399, and then just the top of 400, it talks about the final answer. So they define this new area functions, right? Like how we were doing before. And we're going to be calling that this 2 pi r L. And this is what we're going to be using inside the integral. Another way of looking at this, other than how the book describes it, is you see this first 3 terms here, right? Well, what does that look like? That's the circumference of a circle, right? So basically what we're doing is kind of almost like a disk method, like how we were doing before with volumes, except now we're using this circumference of a circle. And this L comes in because it's not a static circumference, right? It's always changing. And this L is this arc length term that we're going to be using. It's that whole radical with the derivative inside. So putting these things together, we can kind of formulate what we're actually looking into in terms of surface area. So we're going to call, and the book has S for these integrals. So we go from A to B, and we got 2 pi, and then we're going to use this radius here, and that's going to be our f of x, and then our L is going to be this radical term from our arc length. Right? Doing this in the y direction, you can go from C to D, 2 pi. Now, in terms of y, f of x is just y, right? And then we have the L in terms of our definition from the previous section for y, where it's the function solved for x and then take a derivative with respect to y. Now, I should point out that these 2 expressions are only for when we're rotating around the x-axis. Right? So if we're rotating around the y-axis, these kind of get flip-swapped. So instead of putting an f of x here and a y here, for the y-axis, we're going to be having a f of y and then an x, right? So they kind of just flip-flop. Why that comes about is back to the this pink-purple thing that I was talking about. Let me go ahead and highlight that more. This guy right here, that R changes, right? Because we're going from a different direction now. So whenever you're rotating around anything, just kind of draw a little bit of a picture and see what our radius of the circle that we're taking the circumference of is. So that's going to lead us into our example. So let's go ahead and do number 4. So y is equal to 9 minus x squared. We're going to go from -2 to +2 in terms of x. And we're going to be rotating around the x-axis. All right, so I'll give you guys a few minutes to set that up and start trying to solve it, and then we'll go over it. All right, so first thing to do is to find our dy dx. And for that, we're going to bring down the power. What's inside with the new power. And then the derivative of the inside, negative 2x. Simplify this guy a little bit. Those halves and that 2 are going to cancel. So negative x on the top. And then in the denominator, we're going to get a 9 minus x squared. Okay. So let's go ahead and put in the radical first and then kind of simplify it instead of going ahead plugging in the integral, because now we've got some extra terms as well. So we've got this radical 1 plus pi prime squared. This is equal to square root of 1 plus this negative x over the radical of 9 minus x squared, square this whole thing. So we can simplify a little bit. On the top, we're going to get just x squared. And on the bottom, that radical cancels. So we get just the radical of 1 plus the quantity x squared over 9 minus x squared. We can simplify this guy a little bit further by finding a common denominator and just adding those things together. So we get the radical 9 over 9 minus x squared. That looks pretty nice. So we can simplify that just a step further as 3 over the square root of 9 minus x squared. Right? So now we can start trying to plug this into our integral. We've got this s, the integral from negative 2 to 2. And now we've got 2 pi. And because we're rotating over the x-axis and we're doing it in terms of this x, we're going to have this f of x term, right? Because that's going to be our radius. So that's actually back to 9 minus x squared and that radical. And then we multiply it by what we had for that one radical term that we normally have for arc length, which we found to be 3 times the radical of 9 minus x squared dx. Lucky for us that these radicals are going to cancel, right? So then we're left with the integral from negative 2 to 2 of 2 pi. These radicals cancel. That was just multiplied by 3 then, dx. That's pretty easy. That's just 24 pi. So we kind of went through the same methodology of how to start this problem. We found our dy dx here, like we typically do for the other arc length problems. And then we plugged it into what we had for this radical, right? So we square our derivative, add 1 to it, and take a square root. See if you can simplify it as far as you can. So like we did at the end here. And then go ahead and plug it into our surface area formula. And just make sure that you keep in mind what your radius is. So in this case, it was our f of x. If we were rotating around the y-axis, this would have just simply been x, right? Like I said before, these green guys up above are going to flip-flop, where the lower one will be f of y and the upper one will just be x. Right. There's possible to have problems that are rotated around an axis that's neither the x-axis or the y-axis. It could be like y equals 2 or x equals 3. So again, just define what your radius of that circle that you're finding the circumference of is. And then just go through it. So that leads us to this next problem. So number 5 here is y equals the cube root of x. We're going to go from 1 to 2 in the y direction, and we're going to rotate around the y-axis. So the first way we're going to do this is the x definition. So go ahead and see if you can do it in the x direction, and later on we're going to do it in the y direction. And of course they're going to come out to the same thing, so spoiler alert. But we're going to see the differences and why it might be easier to do one over the other. Okay. So the first thing we're going to do is find our y prime. So it's 1/3 x to the negative 2/3. Let's go ahead and plug that into our radical. So we got 1 plus y prime squared. That's the radical 1 plus, we're going to have this 1/9 now, and then x to the negative 4/3. This is kind of messy. I don't particularly like having this negative 4/3, so I'm going to try to simplify this guy a little bit. So we're going to find a common denominator, and that leads us to 9x 4/3 plus 1 all over 9x to the 4/3. Right. We can simplify this guy from the bottom, but we still have the radical on top here, which is 9 times x to the 4/3 plus 1. But now the bottom actually works out and we have 3x to the 2/3. And you'll kind of see why we wanted it in this form in a second. So when we're setting up our surface area, the first thing we'll notice is that we don't have the bounds in the x direction, right? We have it in the y direction, so we're going to have to back up. So in x, we were going from, or I should say, I'm sorry, going from, here we go, y, we're going from 1 to 2. So in x, if y is 1, x is 1, and if y is 2, x would have to be 8. So we're going to 1 to 8. So now we can start writing our bounds. So we have s is equal to 1 to 8. We're always going to have that 2 pi. And remember, because we're rotating in over the y-axis, we're not going to have f of x. We're going to have just simply x as our radius, right? Because if we have some kind of function, I'll kind of doodle something real fast. If we have some function here, and we're rotating around this way, and we're trying to take the circumference of that circle, well, the radius of that circle is just how far we've gone in the x direction, right? So, and then we've got the rest of the term, this L term from the other page. And it's that big messy thing that we found. So it's the square root of 9x to the 4/3 plus 1 all over 3x to the 2/3 dx. So we're going to try to simplify this guy a little bit before we do anything. Equal to 1 to 8. So notice that we've got that 3 on the bottom, so we're going to go ahead and call that 2/3 pi. And now we have an x 2/3 on the bottom, but an x in the numerator there. So this becomes x to the 1/3, right? And we multiply that by the radical, 4/3 plus 1 dx. And now we can try to solve this integral. And so I'm going to do some work over here. So we're going to go ahead and set u equal to 9 times x to the 4/3 plus 1. This means that du is 12 x to the 1/3 dx. So luckily, we have an x to the 1/3, right? So now we have to find what our bounds are going to be. So because our x was 1 to 8, our u is going to be 10, and then 145. Yeah. So they're not the nicest numbers, but they are what they are. So going back to our integral and doing the u sub, we have to divide by 12, and we get rid of that x to the 1/3. So this guy is equal to the integral from 10 to 145 of pi over 18. And then we're just left with the square root of u du, right? Doing this out, we're going to get pi over 27, 145 to the 3/2 minus 10 to the 3/2. So not the nicest end result. Doesn't look like a clean number, but it's an answer, right? So this is kind of messy. I didn't particularly like y prime and then putting in that radical. It looks really messy. And if you hadn't simplified it like I had in what I guess I'll put in orange here, these two steps, you wouldn't have gotten the integral in a nice form to know what to sub out for you. You might have had some trouble. You might have had to do some other kind of integration techniques other than just a simple u substitution. So I wouldn't say that this is the greatest setup. So why don't you guys try to do it the other direction with the dy instead of the dx and see if you can come up with a simpler way of doing this. Spoiler alert, it's actually a lot easier. It's just a few lines rather than this jumbled mess. Okay, so doing it the other way, let's go ahead and set it up. In this case, instead of y equals the cube root of x, got my highlighter instead, we have x equals y cubed. Already looking a lot better, right? So now finding x prime, we just have 3y squared, and then plugging into our radical, we get 1 plus 9 y to the 4th, right? So this is a lot cleaner than what we had above, and we can actually use 1 to 2 now, right, as our bounds, because we're going in the y direction. Going y to 1 to 2, and then 2 pi y cubed, because remember our radius was horizontal, right? So instead of just using x, we have to get what x is. And from above, we knew that x was y cubed. Okay, and then get this radical guy in there, 1 plus 9 y to the 4th dy. And we're still going to have to do u substitution, so we're still going to kind of get the same form as what we did last time. So if we set u equal to 1 plus 9 y to the 4th, our du is going to be 36 y cubed. So we have a y cubed, so that's good. So now for our different bounds, we were going, so y was 1 to 2. That means u is going to be going to, if we plug 1 in, and we get 10, and you plug 2 in, 145. So it looks pretty familiar, right? So now we've got this integral. This is equal to the integral from 10 to 145 to pi. And then we have to divide by 36, right? So 2 over 36, when we back up, that's just pi over 18. And then we got rid of our y cubed, and then all we're left with is the square root of u. And should look familiar. This guy is the integral that we had up here. These two guys in blue. So of course, they come out to the same thing. Pi over 27, 145 to the 3/2 minus 10 to the 3/2. I liked the y direction a lot more. It wasn't as strenuous. It was very straightforward. Like I said, for the up above part, that orange step at the top was kind of needed so that the integral took a nice form, so that you knew exactly what to do for your u substitution. Not to say that the integral was completely unsolvable. If you had simplified it like that, you might have just taken a lot longer of a route to get to that answer. So I like polynomials. So if you've got something like that cube root of x, maybe it's better to do it in the y direction, right? So you have something with a polynomial. So there's definitely something you could do there for a u substitution later on. That's a lot more straightforward. Okay. So those are all the examples that I had for this recitation. Do you guys have any questions about arc length and surface area? So using arc length and rotating it around an axis. Or maybe another question. Otherwise, we can go over something that I really enjoy. We can go over something called Gabriel's horn. Yeah, let's do Gabriel's horn. So it combines some things that we learned earlier on with doing these improper integrals, but now we're doing areas and or volumes and surface areas. So consider the function f of x is 1 over x. Good old 1 over x. Let's look at, we got 1 to infinity, right? Let's go ahead and find out what the volume and the surface area of these guys are, or this whole thing. So if you remember right, what 1 over x looks like, looks something like that, right? And now if we're rotating it around, we got something like this. Try a little bit better, right? And then we're taking all these little circles here, and we're going to try to fill this guy in. So a really good way to do the volume is to do like a disk method, right? So we can set up our integral, the 1 to infinity, and then we have our pi, and our radius for these guys is just going to be 1 over x, right? So that's 1 over x squared dx. From a previous chapter, you guys know that that actually converges, right? If you remember what it converges to? Maybe. All right, well, we can do it. So remember, the first thing to do with these is to have a limit. Limit b approaches infinity, 1 to b, pi over x squared dx. So remember to keep writing your limits. B approaches infinity. And then we've got this pi. We'll take the integral. We've got 1 over x. And then evaluated from 1 to b. And then this guy is equal to, as b goes to infinity, that first thing gets really, really, really small, right? Ooh, that should be a negative right there, right? So that guy is going to be going, whole thing is going to be going to 1 times pi. So we have a volume of pi, right? Pretty cool. We've got this whole thing, and we're rotating around, and it goes from 1 to infinity. That whole volume is finite. It's pi. All right. But what about its surface area? So let's take a look at its surface area. So first off, we're going to have to find f prime, right? So we're rotating around the x-axis, so keep that in mind. And the derivative of this guy is -1 over x squared. So that means our radical looks like this guy here, 1 plus 1 over x to the 4th, right? Square that guy, plug it in. We still have the same bounds, so let's go ahead and look at the surface area. We're going to 1 to infinity, 2 pi, and our radius is going to be our function, right? So it's 1 over x, and then we have the square root here, 1 plus 1 over x to the 4th dx. So I'll give you guys just a little bit and see if you guys can do this integral. And then we can look at some weird phenomenon between the volume and the surface area. Okay, so if we can prove that this guy is convergent or not, we can show some cool stuff about the surface area. So let's do a comparison test. Well, we know that 1 is actually strict, so it's just less than the square root of 1 plus 1 over x to the 4th. This radical, as long as x is positive, which not 0, which we're going from 1 to infinity, so we're okay. We can divide both sides by x, making sure that x is positive again. And we know that the integral of 1 over x dx from 1 to infinity is divergent, right? It diverges. So what does that mean about the integral that we've got up here? Well, this is also divergence. This also diverges, which means that the surface area is infinite, but the volume is finite, which is a really weird property for a shape to have. So go ahead and think about that until next time, and I will see you guys next week.